Okay, so that means the cutoff frequency is 1/2TS. That's in real frequency, not any given. So the Fourier transform just looks like this. In terms of omega, it's minus 1/TS, pi/TS. You have to do 1 there and 0 everywhere. Okay, so what happens? We have our noise, N of t, comes along, and it encounters this low-pass filter. And on the other side, we're going to call this W of t. So what can we say about W of t with respect to N of t? Well, for one thing, we know that Sn of j omega is n0/2. On this side, what becomes of the power spectral density? How can I express the power spectral density W of t? SW of j omega is equal to, okay, last time I pointed out the following property. If you take a random process, Whiteson stationary random process, and pass it through a linear filter, the power spectral density of the new process is the power spectral density of the old process times the magnitude squared of the filter transfer function. So in other words, SW of j omega, power spectral density at the output of this filter, is Sn of j omega, magnitude HLP j omega squared, which is, what is this? What's Sn of j omega? It's n0/2. And HLP of j omega is this rectangle. Therefore, this is given by n0/2 for frequencies less than pi/TS and 0 for frequencies greater than pi/TS. So now, as you might expect, the white noise is cut off at the Nyquist frequency, and over the range of over the sampling range, the power spectral density is constant. So why did I do that? Why do I care about the power spectral density of W? Well, now what I have, so I had N of t goes to low pass filter. And I have W of t. And after the low pass filter, I do analog to digital. And then I get W of k. And what I really want to know is, what's the variance of W of k? Well, what am I doing with W of k? Basically, I'm just taking samples of W of t. So therefore, if this is Whiteson stationary, since N of t is Whiteson stationary, W of t is Whiteson stationary. Since W of t is Whiteson stationary, the variance of this process is constant with respect to time. So therefore, whatever the variance is here variance should be the same over here because these are just points of this function. So variance of WK should be equal to variance of WT, the continuous time random process. And we know this. So I went to some, I went into the frequency domain to do this. Can anyone see a way to extract the variance from here? I mentioned this last time. So variance, remember you can extract the variance from either the autocorrelation or the power spectral density. Here's how. I mentioned this last time. Variance of a process WT is equal to the autocorrelation of that process at 0. So remember that. This is because autocorrelation at 0 is equal to the expected value of WT plus tau, but in that case it's T plus 0, which is the expected value of WT squared. Oh, by the way, this only works if the process is 0 mean, which this one is. And how does that relate to the power spectral density? What's the relationship between autocorrelation and power spectral density? What do I do to the autocorrelation to get the power spectral density? Anybody? Anybody at all?
1 by 2 by.
I'm looking for two words here. Fourier transform. Take the Fourier transform. That gives me the power spectral density. So Fourier transform of RW0. Excuse me. The Fourier transform RW tau is power spectral density. Okay, what does that mean? Fourier transform of RW of tau. Remember this, integral from minus infinity to infinity, RW of tau, e to the, actually this is now a dummy variable, let's call it u. Sorry. Actually, I'm going the other way. Okay, if the Fourier transform of this is that, then obviously the inverse Fourier transform of SW of j omega is the autocorrelation. The inverse Fourier transform of the power spectral density is this: 1 over 2 pi integral minus infinity to infinity over omega of SW of j omega e to the j omega tau d omega. Like that. Now if I want, and this is equal to RW of tau, if I want RW of 0, which is equal to variance of WT, all I do is I substitute 0 in for tau, and then I get 1 over 2 pi integral from minus infinity to infinity of SW j omega times e to the j omega 0, which is e to the 0, which is what? What's e to the 0? 1. D omega. So in other words, if I just integrate over the power spectral density, I get the variance. So that's super convenient here because the power spectral density is a rectangle. So it's very easy to integrate over a rectangle. So in this case we have